Hello everybody. So we are going to start now the discussion on the calculation of the head losses in case of turbulent flow. And actually what we are going to see here is very similar to what we did in chapter in the laminar flow. So we know that based on the dimension analysis that delta P is going to be L over D times rho U squared times function of Reynolds number and epsilon over D. And in the laminar flow discussion, we agreed that this F or delta P is calculated using this equation, which is Darcy's equation, and this F is going to be the function of Reynolds number and relative roughness. For laminar flow, we found that experimentally the relative roughness has no effect, so it was only function of Reynolds number, and this is why the calculations were very straightforward and simple for laminar flow. But for turbulent flow, we will see that both of these parameters or dimensionless numbers will have effect. And now we are going to see how we can calculate this friction factor. So it's got experimentally. We already have the results of the experimental tests that have been done. And the result is, actually, this is not only the result. There are a lot of equations. If you check the literature, you'd see that there are a lot of equations that have been developed to calculate the friction factor for turbulent flow as a function of Reynolds number and epsilon over D. But many of them are valid for special cases, for special shape of or pipe shapes, for a special range of Reynolds number or whatever. But the equation that we are going to use in this chapter is a very famous equation, because it's valid for, if not all of the cases, it's most of them. And this is called Colebrook equation. And it's of course it's expected that the equation would be a complex equation compared to the equation of laminar flow, which is constant over Reynolds number in this case. So in the case of turbulent flow, you'd see that the equation is much more complicated for calculating the friction factor. First thing to notice is that here is epsilon over D and here is Reynolds number. So friction factor is dependent on both. The second thing, which is a very important thing, that this equation is an implicit equation, which means that the friction factor is here and is also here, which makes it impossible, mathematically impossible, to have the friction factor on one side and the rest of the parameters on the other side. Even if you try to rearrange the equation, you will reach a case or a form where you have, instead of having square root f is 1 over square root f is a function of log something that has friction factor, it would be this friction factor is function of 10 power this friction factor. So it's not impossible to have the friction factor separated on one side. And this kind of equation is called an implicit equation, which the variable cannot be calculated directly from the rest of the parameters, and it has, or it appears on both sides of the equation. And the implicit equations are not solvable using direct calculations. It has to be solved by trial and error, and this is something we'll discuss later, inshallah. So for now, this is the equation that we have, and the equation, as we said, it's function of Reynolds number, which is rho u d over mu. We know all of these parameters. We have discussed Reynolds number before, and of epsilon over d. And epsilon, as we said before, is the surface roughness, which is the average height of the irregularities of the surface of the inner surface of the pipe. And for the value of the surface roughness, it's already available in tables. So it's nothing that we do by ourselves or calculate by ourselves. It's just in tabulated data, in tables. And this is a function of the material itself. So that's why we have it in this table. So based on the type of material, it will have a roughness value that has been tested and measured before. So you just go to the table, pick the value. The values here, as you see, there are two values in 2 units, in feet and in millimeters. So you pick the value that is suitable for your calculations. These values are for new pipes, which means that the pipe is still new, the inner surface is still not affected by the fluid flow. And as time goes, for some fluids, the roughness might increase. And the reason is either that the fluid is causing fouling, which means that there are materials from the fluid that precipitate on the surface, or deposit on the inner surface of the pipe, which increases the surface roughness, or because the corrosion. So maybe the material that is flowing is causes corrosion in the inner walls of the pipes, in a way or another. One of the very famous things is or cases is the hydrogen pitting, which is if the fluid flowing is hydrogen gas, then it will react with the metal and cause like some holes in the inner wall of the pipe, which causes more roughness than the initial roughness. So in this case, usually the typical value for the roughness increases from 5 to 10%. So this is what happens as time goes, and that's something that has to be taken into account when we design pipes, because we install a pipe that should be used for 10, 20 years or more. So you have to plan for this beforehand. I have this other table here, which is from another textbook. It's the same thing. It's the roughness in millimeters, but it's giving the values in millimeter and in inch. It's giving ranges for all of them and the recommended value. So for instance, if it's brass, then it's from 0.01 to 0.0015. The recommended value is 0.002. So it gives more ranges and more types of materials than in the original or the table that I showed you before. This previous table, which you see here, is the one in the textbook, while this table is in another textbook. The name is at the bottom here. It's Ron Darby, Chemical Engineering Fluid Dynamics. So it's already here. So it's useful in case you need them. So this is the equation that we are going to use, which is the Colebrook equation, and the ways we can extract or get the friction, the surface roughness, to put it in the equation to calculate the friction factor. There is one more option or alternative for this equation. Of course, dealing with this equation is not like a fun thing, especially if you don't have a tool to do the calculations. So if you don't have a calculator or a computer software that you can use to do the calculations, it's going to be very difficult to do these calculations manually to get the friction factor. So there is one other option, which is a chart. And this is something that we mentioned in chapter 7 when we were discussing the advantages of using the equations in dimensionless form. And we said that the dimensionless equations are more universal, and they rule out the effect of the size of the system. And this makes it possible to put the equation in form of a chart. So we can, and we saw the chart in the fraud number example. So for this chart, you can just go with extract data from the chart without doing any calculations. And this is what we're going to do starting next video. But before we go through this, there is an introduction that I will go through, which I think is a very basic concept that I want to discuss. But it's very important to make sure that you have this in mind, to understand it well before we go through the chart and see how to use it. So I will stop here and we'll continue next time, inshallah. So I'll see you then.